Welcome. In this video, I'll explain how to use the RSA algorithm to encrypt and decrypt information. First of all, RSA has a lot of meanings in the security world. First of all, it's the name of this algorithm, which is probably the most widely used encryption algorithm in the world. Secondly, it's also the name of a company, RSA, which was founded to market products that used RSA back when it had a patent. And it has since developed many products, including two-factor authentication key fobs like these. And it's also the name of an annual conference that's held every February in San Francisco. But originally, RSA came from the names of these three MIT professors, Ron Rivest, Adi Shamir, and Leonard Edelman, and their last names formed the acronym RSA. So the algorithm itself was invented in 1977 and was published the following year in the Communications of the ACM. This is the paper. And it was a groundbreaking piece of research. And what was so groundbreaking about it was that for the first time in history, we had a system to encrypt with one key and to decrypt with another. So in this case, we have one public key to encrypt, and then the private key would decrypt. And the inverse was also true. So a private key could be used to encrypt, and the public key would be then used to decrypt. So to remind you about inverse functions, the inverse of any number times itself is 1. And this is useful for encryption. For example, let's say we have a secret message 7, and I want to encrypt this secret message by multiplying it by another number, in this case 328. So the result of this is a larger number, and it's not clear that 7 is a part of this number. So it's obfuscated. It's encrypted, let's pretend, in the number 2296. But if I multiply 2296 by the inverse of 328, I get back to the secret number 7. So this is the RSA algorithm, the one used for encryption. You take a message m raised to the eth power, and then you take the modulus of that result for the number n, and the result is your ciphertext. And this is the decryption function. You take the ciphertext, raise it to the power d, mod n, and that results in your plain text message. So if you look at both of these together, you see that one is undoing the effect of the other. Now, all of these different variables here, two of these, E and N, form the public key, the key that's shared with the world, that can be published on the web or anywhere. And the exponent D is the private key, the number that must be kept secret for this scheme to work. So RSA is called a one-way trapdoor function. And what this means is there's no way to undo the encryption function unless you know the trapdoor. And in this case, the number n is the trapdoor. So the question is, why is it difficult to find n, or the trapdoor in n, since it's published to the world? And the answer is prime factorization. And this gets back to the fundamental theorem of arithmetic, which holds that any number greater than 1 can be written in exactly one way as the product of prime numbers. So for example, the number 15 can be written as the product of the prime numbers 3 and 5. Or the number 255 can be written as the product of 3 primes, namely 3, 5, and 17. So for example, it's easy to find the product of two large prime numbers, but it's very hard to take a very large product and factor it to find the two primes that compose it. Now let me show you a real-world application of this. This number here is my PGP public key, or in other words, the variable n. It is a 4096-bit number, and here it's expressed in decimal form, and you can see that it's huge. Now the question is, what two prime numbers multiplied together result in this large number n? And this is a problem which is supposed to be impossible for the world's computing resources to solve for many, many decades. In fact, 50 years is probably a low estimate. So knowing the factors of n is the trapdoor in this trapdoor function. If you know the factors of n, you can decrypt a message that's been encrypted with the public key. Now you try. So here is the algorithm for encryption and decryption. And here's the message for you to encrypt. In this case, the secret is the answer to the ultimate question of life, the universe, and everything, or in other words, the number 42. And I'm giving you two primes, 61 and 53, represented by P and Q. I'm also giving you E, which is 17, and N, 3,233, and D, which is 2,753. So I'll explain how to calculate these constants later, but for now you can use them to encrypt the message and decrypt. So try that out. Put this video on pause. Okay, let's check your work. So to encrypt, we have 42 raised to the 17th power. This is the variable E, mod n, or 3,233, and that gives us our ciphertext result. If we were to type all of this into Wolfram Alpha and calculate it, it tells us the result is 2,507. So there we are. This is our ciphertext. Now for decryption. So we take the ciphertext, 2,557, raised to D, which is 2,753, mod n, which is 3,233, and this should give us back to our plain text message. Again, typing this into Wolfram Alpha, we get this result, the plain text 42. So the question is, how do you choose your own values of n, e, and d? So in the previous example, I gave you these variables, but how do you calculate these for yourself so you can use RSA in your own system? Well, first you choose two very large primes. Second, you calculate a constant, phi, which I'll explain, and you choose two exponents, e and d, in a very specific way, which I'll also explain. So first, choose two very large primes. So these primes, represented by P and Q, when multiplied together, give us n. So the question is, how large should P and Q be? Well, again, back to my example of my public PGP key, this is 4,096 bits, which means that P and Q are each 2,048 bits, and multiplied together, these two very large prime numbers result in n. It's important that n is a very large number. The conservative recommendation currently is that it be at least 4,096 bits long. So the second step is to calculate phi. So phi is a mathematical constant which stands for the Euler-Totient function, which is named after one of the great mathematicians of all time, Leonhard Euler, as commemorated on this Swiss franc bill. So we need to find a number phi so that almost any x raised to phi mod n will result in 1. This is important because it will allow us to derive the inverse of e. Phi is calculated as the product of p minus 1 and q minus 1. It also has the limitation that phi must not share a factor with e. So you just have to check this before you continue using the algorithm. So the final step is to choose exponents e and d. So first you can choose a small e. It just has to be greater than 2, and very commonly e is 3. It's a constant in many systems, or 5 or 17. The difficult part is finding the inverse of e, which is d. And specifically, it has to be the inverse of e mod phi. This is the algorithm for this. E times d mod phi gives us 1. If this is true, then we have found the inverse of e. Now to do this, we're going to use an ancient algorithm created by the mathematician Euclid, another one of the luminaries of mathematics. This particular algorithm, which he designed well over 2,000 years ago, is called the extended greatest common divisor algorithm, or the extended Euclidean algorithm. And I'll explain how this works. So we start off with our very large primes 5 and 11, and we set e to the value 7. And now our task is to find its inverse. So first we find n, which is the product of p and q. So 5 times 11 is 55, so n is 55. Now we find phi. So phi is p minus 1 times q minus 1. And in our case, this gives us 40. So phi is 40. Now the task is to find d. And this is where we use the extended Euclidean algorithm. We have to find d so that e times d mod phi is 1. There are formal ways of expressing this algorithm, but I'll show you a shorthand way of doing this, which you can use to calculate d using phi and e. First, rewrite a table consisting of 2 columns and 2 rows. In the top row, we write the number phi, in our case 40, in both columns. And then in the second row, we have the variable e, and in the second column, we have the number 1. So you always start off this way with phi, e, and 1. So you start off by dividing phi by e, or in our case, divide 40 by 7. And this gives us the number 5. Now we multiply this result 5 by 7 and by 1 to give us 35 and 5. Now we take these two results and we write them below 7 and 1 in each column. Now we subtract these results from phi in both columns. In this case, 40 minus 35 for column 1 and 40 minus 5 in column 2. And the result of this we write below in each of the columns. And now with this third row, we can remove the first row so that now we have a new row 1 and a new row 2. And we start over. Again, we divide 5 into 7, which goes in 1 time. And now we multiply 1 by 5 and 1 by 35. We subtract 5 from 7, and we subtract 35 from 1, and this gives us 2 and negative 34. Now with this negative result, we have to do one additional step, which is to take its modulus. So negative 34 mod 40, or mod phi. And to do this, we simply add these two numbers together, negative 34 and 40, to give us a positive number. In this case, 6. So you write 6 in column 2, and once again, now we have 3 rows, and we can eliminate the first row, and we do this one more time. So 2 goes into 5 2 times, and we take this result, multiply it by the numbers in the second row, and this gives us 4 and 12, and we subtract. So we have 1 and 23. Now, this number 1 is a special result. When we get 1 in the third column of column 1, that tells us that we have arrived at our result, which means that 23 is the value for D. And we can check our work. So here is the formula. E times D mod phi results in 1. So in our case, here are our values. 7 times 23, our derived D value, mod 40 results in 1. So it checks. So here are all the variables we need to use the RSA algorithm. Our public key is E and N, or 755. And our private key is D, or 23. Now you try. Use these primes, 89 and 107, and E as your exponent. Now find phi, and using phi, derive D. You can pause this video, and then we'll go over the solution. Okay, let's check your work. So n is p times q, or in our case, 89 times 107, and this is 9,523. So now that we have n, let's calculate phi. So p minus 1 times q minus 1. So phi is 9,328. And now we find d. So again, here's our formula. E times d mod phi equals 1. So again, using the extended Euclidean algorithm, we write phi in the first row in both columns 1 and 2, and in the second row, column 1, we write the variable e, and in the second column, row 2, we write the number 1. We see how many times 3 goes into 9,328, and we get this result, 3,109. Now we multiply 3,109 by 3 and also by 1, which gives us these results. We subtract our numbers from row 1 and get this result. Now this is much faster because we arrived at 1 in the first step, which means that D is 6,219. So again, checking our work, E times D mod phi is 1, so 3 times 6,219 mod 9,328 equals 1, so it checks. So now let's talk about RSA as used in real life. So RSA is about 1,000 times slower than symmetric crypto systems like AES. And for this reason, RSA has been used from the very beginning in hybrid crypto systems, or systems that use a symmetric key or secret key algorithm and an asymmetric or public key algorithm. Probably the most common hybrid crypto system is your web browser. If you visit Amazon.com using SSL and click on the padlock in the top left, you will see this connection information. In this case, the connection is encrypted using RC4, a symmetric encryption algorithm, using a 128-bit key, and it uses RSA as the key exchange mechanism, which means all RSA is used for in this case is to encrypt the symmetric key, the RC4 key, and send it to the recipient. Once this key is received, the SSL session switches over to using RC4. But RSA is used for more than just key exchange. If we click on the link for certificate information, we see this. In this case, the Class 3 certificate authority at the top signs the VeriSign G5 certificate, and the VeriSign G5 certificate authority signs the VeriSign Class 3 G3 certificate. If we scroll down for details, we can see Amazon.com's RSA public key, which we can see is 2,048 bits, or as represented here as 256 bytes. And those are the steps to use the RSA algorithm. Hope you found this useful.